Okay. Um, so, so we were talking about hypothesis testing. Um, let's continue with the example. Let's make a recap. So remember, we were talking about lifetime of people in Turkey, right? So Turkey has a population of over 80 million, and I'm interested in the average lifetime of people in Turkey. So what I'm trying to do is to find or to infer information about the real but unknown parameter mu. Okay? So it turns out that I just go to Zincirlikuyu Mezarlı and record the age of death of 100 many people, and it turns out that their average is 71.8. Okay, and I want to test whether the real mean life is 70 or not. Okay, so the unknown, whether the unknown parameter mu is equal to 70 or not. How about 71.8? Well, that's the average of a sample. So x bar is equal to 71.8, okay? And I want to test whether mu is equal to 70 or not. So we will assume that the standard deviation of life or people's life in Turkey has a standard deviation of, 8.9 years. That's a weird assumption, but later we will relax this assumption and we will study cases where we don't know sigma. So, well, there is an evidence, there is a data, which is X bar. X bar says that, well, the real mean is not equal to 70, okay? So what does this mean? This means that, remember, if you want to test this again, mu is equal to 70, and if it turns out that X bar of 100 many people is exactly equal to 70, then there's no problem, right? You won't test anything. You won't say whether I want to test whether mu is equal to 70 or not, because the data that you have already says that your data says that mu can be 70, nothing else. But here, X bar, the observed value of the sample average is 71.8. Okay, and well, there is a difference between this mu and X bar, which is equal to 71.8. And I want to see whether this data, this evidence is strong enough to say that, well, the real mu is equal to is not equal to 70. If it is not that powerful, if it is not that strong, if this evidence is not strong enough to say that mu is equal to 70, then we will conclude that, well, if the average lifetime of population is equal to 70, then we may have a sample whose sample mean is 71.8, okay? So we will use a procedure which is called hypothesis testing to test this conjecture. So a statistical hypothesis is an assertion or conjecture concerning one or more populations, or let's say populations parameters. Okay, generally we just deal with the parameter of the populations. So how to do this? Well, uh, we will have two hypotheses in a hypothesis testing procedure. The first one is a null hypothesis, which says the conjecture mu is equal to 70. Okay, and the second one is the alternative hypothesis, which is the complement. Okay, the complement of H0. Right? um, you may say you may have two decisions after the test. We will see how to make the test, but at the end we may have two decisions. You will either reject H0 in favor of H1. So what does it mean? You reject and say that, well, I reject H0 and say that mu is not equal to 70 because your evidence, so in our case, the evidence is X bar, is strong enough to say that mu is not equal to 70, or you will fail to reject. Well, students generally prefer to say you just accept H0. Well, statistically, there's nothing as accepting H0, but in order to keep this in mind in a more easy way, you may say that. You just say accept H0 because well, the data is insufficient. So in fact, what does this mean? Well, what does this mean? Let me just say this is 1 and this is 2. So if you just say 1, if you just say 1, uh, if you just decide in 1, um, it says that, well, um, if the mean is equal to 70, then observing an X bar of 71.8 is not very possible. Okay. Again, what does this mean? If the average lifetime of people in Turkey is 70, then observing an average lifetime of 71.8 years for 100 many people is not very possible, is not very probable. Hence, you just say that, well, you just reject H0 and say that, well, this data suggests that mu is not equal to 70. Because, as I said, if mu is equal to 70, then well, there's a problem with X bar. It's very improbable. So if you just say the second one, then in fact you just say the vice versa. You will say that, well, if mu is equal to 70, then you may observe 71.8. Okay, is possible. Is possible. Hence, you don't reject H0 and say that, okay, mu is equal to 70. It can be mu can be 70. Okay, so how to decide on this, whether it's possible or not? Remember, we just talked about being close enough, X bar and mu. But what does close enough mean? Okay, so a clever way is the following. Assume that, well, assume that the null hypothesis is true. Okay, what does this mean? This means that assume that null hypothesis, which is mu is equal to 70 in our case, assume that this is true. Assume that I say the lifetime of people in Turkey is 70. Assume that, well, your teacher, your professor is correct. Okay, so then what is the use of this? What is the use of this? Now, just go back about our discussion about X bar. We said that X bar is approximately normally distributed with mu of X bar is equal to mu and sigma of X bar is equal to sigma divided by root n. Okay? Sorry, this is something like this. Okay? Okay. Now, so so X bar is a random variable, right? It's a normal random variable. If you know the parameters of X bar, you can just plot it, right? You can just plot this. Here you have the mu of X bar. Well, this is the sigma of X bar, okay? Well, if you know the distribution, you can just plot this. After plotting this, well, I have an observed value of X bar. Remember, X bar observed, which is, in our case, that's equal to 71.8, right? What I can do is, well, this is an observed value of the random variable X bar, okay? This is an observed value of the random variable of X bar, okay? So X bar is a random variable, okay? And this is an observed value of this, 71.8. Okay, so then what you can do is just put 71.8 into the plot. I don't know, if it is here, let's put it here and try to see if, so this is the distribution of X bar, then try to see what is the probability of observing 71.8. Okay, so this is something that you can do. Well, okay, but do you know the distribution of X bar? Well, yes, the distribution of X bar from center limit theorem, okay, I know that it's normal distribution, okay, here. Now, how about mu of X bar? How about mu of X bar? Do you know it? How about sigma of X bar? Do you know it? Well, sigma of X bar in the question that's given, right? Because in the question it says that, well, sigma of people is 8.9. You are just taking 100 many people, which means in square root of 100, which means sigma of X bar is equal to 0.89, right? How about mu of X bar? Do you know it? Well, before hypothesis testing, I don't know anything about mu. But in the hypothesis testing, remember what we say. We say that, well, assume that null hypothesis is true. If you assume that null hypothesis is true, okay, so just look at here. Null hypothesis says that, well, mu is equal to 70. If you assume that this is true, then automatically mu of x bar is equal to 70 as well, right? That's great. Now, what you have is that mu of x bar is equal to 70, sigma of x bar, you already know it, so that's equal to, just look at here, that's equal to 0.89. Well, that's the distribution of the random variable x bar, okay? That's great. That's the distribution of the random variable of x bar, right? So under this hypothesis, we know the distribution of x bar, okay? Then again, you know the distribution of x bar. So what you can do is just put your observed value, onto the plot and try to see whether this is an extreme value in this probability distribution or not. If it is an extreme value, which means the probability of observing this is low, then you will say that, okay, sir, I assume that your conjecture is true. Under this conjecture, I just plot the distribution of x bar, but it turns out that under this distribution, observing 71.8 has a very low probability. Hence, since 71.8 is my data, is my observed data, I suspect your conjecture, okay? Hence, I reject the hypothesis. This is what we will do, okay? So, okay, now, okay, that's great. So we talk about this. Well, one problem is that, well, how do we define a point to be extreme? Okay, so what does an extreme point mean? So again, let me just plot the distribution of x bar. Okay, so here I have 70 and the sigma of x bar is equal to 1. That's great. This is mu of x bar that's equal to 70. Let's assume 71 is somewhere here, okay? So how can you say that 71.8 is an extreme point or not? Well, um, in fact, in every question, we will be given the definition of extreme points through the significance level alpha, okay? So alpha, which is defined as the significance level, will, uh, will define as the extreme points. How? Uh, Let me just continue. So if the significance level is given as alpha is equal to 0.10, right? Then what you do is you just divide alpha into 2, so 0.05 here, okay, so this is 0.05, and 0.05 here, okay, this is 0.05. So if you just sum them up, 0.05, 0.05, that's equal to 0.10. It means that, well, the extreme points are the 0.05 or the 5%, right? This is the 5%, and 5% here. So what I assume is that the 5% of the data to the right, at the right tail, and 5% of the data at the left tail are the extreme points. Hence, I just call to say I love you, okay? Not of course. So I just call these regions are the critical region, okay? Critical region, right? This is the critical region. This is the critical region. Why? This is the critical region because if you see some observations in this region, it means that, well, the probability of observing something is very low. It's an extreme point. Hence, we can just reject the hypothesis. Okay. So if your X bar observed is there, then you can just reject H0. In general, we just pick alpha as 0.01, or you can say that's 1%, or 0.05, 5%, or 10%, okay? So these are the general definitions of extreme points, okay? Um, okay, so we can solve the question with different definitions of extreme points, okay? So let's solve it with alpha is equal to 0.10, okay? Alpha is equal to 0.10. Then what we will have is that I will just have this, okay, and this. So 0.10 means that, well, here I have the 5%, 0.05 here, or again, 5%, they are the same here. And I will just put 5% here, okay? This is the 5%, which is equal to 0.05. And what I will try to do is just find the, the points here, okay? So that to the right of this, you have the 0.05 of the data, and to the left of this, you have the 0.05 of the data, okay? Okay. Um, okay. So what I can do is I will try to see whether 71.8 is it here, okay? Is it here, 71.8, or is it somewhere here, okay, 71.8. If 71.8 is here, then you will reject H0 because it means that your observed X bar is in the critical region. If 71.8 is here, it means you do not reject, right? Do not reject H0. Okay? So how to find whether 71.8 is in the critical region or not? What you can do is just find this point, okay? So let me just put this center here. This is 70, okay? So let's say this is, let me get this point as B, okay, small b, and let's say this point as A, right? So how to find B? B is a point such that probability that X bar is greater than B, that's equal to what? That's equal to, by definition, that's equal to 0.05, okay? And just convert this probability to standard normal, X bar minus mu of X bar divided by sigma of X bar greater than B minus mu of X bar divided by what? Sigma of X bar. This is equal to 0.05, okay? So let me just divide it like this. That's great. Now what is this? X bar divided by mu of X bar divided by sigma of X bar. X bar is a normal random variable. You just subtract its mean and divide it by its standard deviation. Hence, this is Z. Probability that Z is greater than this value, B minus mu of X bar divided by sigma of X bar, okay? This is equal to 0.05. So remember we just use subscripts. Remember subscripts. So this is the Z value, which leaves an area of 0.05 to the right, okay? So this is in fact Z sub 0.05, right? So from here, I have B is equal to mu of X bar plus Z sub 0.05 times sigma of X bar. In fact, this is a general formula, okay, just for converting the standard normal to any normal random variable. So from here, B is equal to, remember, mu of X bar is 70 plus Z of Z sub 0.05. Well, I don't know, let me just um, Z sub 0.05. Let me just find from my Excel. Okay. So norm 0.05, let's see, 1.645. Okay, so this is equal to 1.645 times sigma of X bar, which is equal to 0.89. Okay, so B is equal to, again, let's open the Excel. So let me just change this so that I have a plus there. This is equal to 70 plus, sorry, plus this times 0.89. That's equal to 71.46. Okay. So this is equal to 71.46. Okay, 71.46. So what does this mean? What does this mean? Let me just re-plot it. This is the distribution of x bar. Okay, this distribution of x bar. Here I have the 70. Well, 71.46. That's where the right of 71.46 is equal to what? 0.05. Remember, so this is B. Well, what is my 71.8? 71.8 is somewhere here because that's greater than 71.46, right? So this is 71.8. What does this mean? This means that 71.8 is in critical region, okay? That's in the critical region. Hence, what we will do is we will just reject the hypothesis, okay? So you can just do the same thing with alpha is equal to 0.05, alpha is equal to 0.01, and so on and so forth. Okay, you can just check this with different values of alpha. But remember, for different values of alpha, well, your observed value 71.8 will not change, but what you will see is this region, okay, this red region, let me just change the color again. So this region will change because, well, this red region has a 0.05 probability to the right, but in this alpha, you will have a 0.025 to the right. And in the third alpha, this one, you will have 0.005 to the right. Okay. So in fact, we just did this for our example. B turns out to be 71.46. Okay. Um, so for this particular example, this is an example where you have 68. So this is for a different question. Okay. So let me just go back. Hmm. So sorry for this. This should be not 68 by 70, right? Um, so here, um, so here, let me just write this. Um, so let's say this is A is equal to 70 minus 1.96 times 0.89, right? This one. And p is equal to again 70 plus 1.96 times 0.89. Okay. Well, this is again, this is the calculation of what? This is the calculation of critical region. Okay. Calculation of critical region, right? For uh, for different value of z, which is z sub 0.025, okay? Or for alpha that's equal to 0.05, okay? Well, 70 minus 1.96, this is 70 plus 1.96, okay? And this is equal to, and this is equal, let me just calculate it in Excel again. So I have, this is equal to 70 plus 1.96 times 0.89, okay? So this is 71.74, and let me just take the other side. So this is 71 point, right? See this? This is, okay, 71.74. So this is 71.74, okay? And the other one is 86.26. 80, sorry, 68.26, okay? So these are the A and B for what? For, again, alpha equal to 0.05. Okay? So 75. Okay, should let me just um, so that it's compatible with the next slide, right? So let me just write it like this, 25 and 25, okay? So it turns out that the rejection region is between minus infinity and, so this is minus infinity, then 68.25 and 71.75 and plus infinity. This is the rejection region, right? So remember, for alpha is equal to 0.05, I have this one and this one, okay? So this region is 0.025 again, and this region is, so let me just shade it, and let's shade it here, 0.025, okay? And it turns out that this is 68.25, and this is 71.75, right? And what is the center? The center is 70, okay? So the right to the 71.75, to the left of 68.25, these are the rejection region. Now let's check our observed X bar, which is 71.8. So 71.8, well, it turns out that 71.8 is where? It's somewhere here, okay? It's in the critical region, hence so it's greater than 71.75. Hence, what you do is we just reject the hypothesis. Okay, remember, reject the hypothesis in what we are saying is that in the favor of, right, in the favor of H1. Okay, in the favor of H1 uh, at a significance level of alpha. Why is that? That's because you just reject the hypothesis uh, by looking at the observed value of the random variable and checking whether it's in the critical region or not. And how you define the critical region? By just looking at the significance level. So for different significance level, you may reject the hypothesis or you may not reject the hypothesis. Hence, what you should say is that when you're just rejecting or not rejecting hypothesis at the conclusion, you should say, I just reject the hypothesis or do not reject it at a significance level of this alpha. So in this particular question for this alpha, I reject the hypothesis. Okay. So our observation, which is 71.8, does not support the conjecture or the hypothesis which says that the real mean is 70. What does this mean? So our data, so what does this mean in terms of daily life? So if the average lifetime of people in Turkey is 70, then it's very unlikely that you have a sample of 100 many people whose average lifetime is 71.8. Hence, what you do is you just reject the hypothesis, okay? Now, in the next video, we will talk about standardizing um, this hypothesis testing.